we're going to talk about the technology to address the biggest challenge to functional camera systems used in pulp and paper systems. And that's light performance, honestly. So our solution, our answer to that is the paired use of near-infrared LEDs with cameras. So this introduces ECS Chalk Talk. Each month, ECS will take a deep dive into the issues that paper makers want to hear. It is, what are the best practices and challenges to maximizing one of the most valuable tools that you have to stay competitive in today's marketplace, and that is your camera-based vision systems. So let's talk about what we mean when I say a functional camera system. And that is what we're going to talk about today. These are the camera systems where the computer's still working, the camera's still working, the backbone is still there. It's providing something to the operators, but it's not providing the value that it needs to. So honestly, paper mills is where these components go to die. And so the lighting technology is that weak link. And that is the one that creates the most frustration for the camera to not work at the proper settings. So two things happen. The camera cannot work at the proper depth of field, shutter speed, cannot work at the right contrast. And then number two, eventually the LED dies. So that is the technology challenge that we're going to talk about today. And that is how you make this part of the chain, this link, provide ultimately the resolution that you need. So where in the paper process is this technology being applied? ECS covers camera systems from the very end to end. The first end would be the chips coming into the paper mill. That's where we're going to be looking at the chips, chip thickness. And then we also have systems all the way at the back end of the paper machine. And that's going to be things like core inspection. That's the pallet right before it goes to Walmart. That is my quality correct before it goes to the last value-added process. Today, we're going to talk about one of the parts in the middle, and that is on the paper machine. So that's where we're going to have the technology for today. And that is not in the chip inspection, not laser inspection, but right there in the middle on your paper machine and also on your converting line. What we will discuss today, starting with the end, we've already seen some images at the very beginning. What does steam, what do IR, what does white light, what do things look like on the paper machines? So these are images from actual camera system installers, and we'll have many more toward the end of this. What is near infrared and what it is not? How does using this type of lighting technology increase the performance of your vision system? Where and when is it most ideal? Let's look at some additional mill use case studies. What is the cost of the technology? And can it be used on non-ECS systems? The majority of the images that you're going to see today are actually on existing systems that are not from ECS, where we just go in and we put this technology on there. So we're saving the camera, the backbone, the computer, software. We're just making it run better with the right type of light. And then at the very end is questions and answers, but please raise your hand throughout any of this. If you have a question that you want during the presentation, I do not mind answering that as we go along. So one of the ways that I talk about technology is kitchen stools and funnels. And this one, the building blocks in the funnel of the technology. There are 10 things listed here. They all funnel down to one thing, and that's the pillar of any camera system, the most important part of what we do and why we do. And that is operator utilization. If we don't get all the things right in that funnel, so it pinpoints to that one thing, you have no contribution to increasing the machine OEE. Operators do not use the system. So of all the circles up there, the blues and the pinks, it's only the pink one that we're going to talk about. But that has so much to do with how the technology funnels down in its utilization in order to give you a performance increase, reduce delay, increase production, reduce waste. LED right there. So terms and concepts that you hear today. How do you define resolution? Is it the pixel? If that's what we're using? Is it the quantity of pixels or is it the quality of pixels? Which one is better? What's shutter speed? What's contrast? Depth of field? Behavior of a light-starved camera? Wavelength? LED cluster? Scattering? Monochromatic? A Fresnel lens? Electronics and heat failure. So this is the next slide, and this starts the actual talk here. So again, we're going to talk about funnels, and we're going to talk about kitchen stools here. Think about the resolution on your system as a big old triangle. And the very last thing that we're going to have down right here is what I call MELT, M-E-L-T. And that's an acronym for maximum even lumens on target. So maximum even lumens. Okay. So why is that important? Well, it's all the stuff that goes into that that's going to equal resolution. All right. Why is resolution important? It's the quality of the pixels that you use as an operator or image processing tools used to make proactive decisions in order to understand the cause of the paper break, or better yet, keeping the train on the tracks before the paper break happens. That's image processing tools. Either way, the quality of those pixels is going to directly correlate to the ability to drive that machine better and faster. So what technology funnel do we have here? Looks like my stuff is backwards. Is going to be these three things. Contrast. Then after that, you're going to have depth of field. And then after that, you're going to have shutter speed. So those are the three items that are going to create that technology funnel in order to drive maximum even lumens on target. So that is on the backdrop of the next one we have here. So in terms of how we employ that out there, we've got these ones right here. So after that, how does the technology funnel relate to near infrared? Well, let's draw that out for a second. Let's talk about that. So out on a paper machine, we're going to draw what you're going to see out there. Number one, on a paper machine, you're going to have a camera. And then on that, you're going to have some sort of LED next to that camera. It's going to be on a paper machine. All right. And then another item, you're going to have steam. All right. And then you're going to have what we call an ROI. Some people call that a region of interest. Some people call that a scene. Another way to look at that is your FOV, your field of view. What is the camera looking at? And then you're going to have the result of these five things above it. What happens when you combine all of that into that nice little sandbox? And then after that, you're going to have the ECS answer to what we know. And then under that, there are 7 elements to what we do in order to deal with what we're about to draw out. That is cameras, lights, steam, paper machine, looking at something. So here's your camera. And here's your LED. The camera has a little sensor on that camera, CMOS sensor. And then traditionally, this is just maybe a pickup suction roll on the front side of your paper machine. You've got your felt right here, and you got your paper right there. And then you have steam. You've got something that is surrounding that right there. And inside that steam is your field of view, your scene. It's what you want to look at, your ROI. It's right here. Boom. So here's your camera looking at that with its field of view, and then here's your LED doing the same thing. So what happens when you use a traditional LED? Well, energy comes out, and the minute it hits that water vapor, it scatters. And it bounces that energy right back to the camera CMOS sensor, presenting it with a wall of white energy. You do not see what's inside of the steam. You do not see the important part of the image. All you see is white steam. So in terms of the ECS answer, number 1 out of the 7, you have to use near NIR. What does that do? Well, NIR, at the wavelength that we use, which is still sensitive to the camera sensor, is a longer wavelength of light. So it's able to penetrate through the water vapor in order to hit my region of interest or my scene, and then bounce back so it can be received by the sensor. But no normal NIR light is going to work, because even though it has the advantage of the longer wavelength, the challenge is I need to produce enough NIR in a certain way that it's able to make it through the steam, not stop at the steam, get here, and then bounce back again. So the second part of what we've got to figure out is the power. And the power of an LED is divided into two distinct places. Number one, I'm going to talk about how we hammer drive the LED. It's called strobing, but it's a hammer drive. And then number two, the power that we can provide through that hammer drive. So let's think of this. This right here on my x-axis is time. My y-axis, we'll call that energy or power. Turns out that when that camera takes its first image, let's say right here, that's 1/60 of a second. And then later, if it's a 60 frame per second frame of our camera, could be 100, could be even more than that. But for this example, we'll say it's 60 frames per second. It's going to take another image. And then at 3/60 of a second, it'll take another image. What the camera's actually doing, though, is the sensor, or the chip right there, is only on for between 50 and 100 microseconds. And then what happens after that? It actually turns off. Then it turns back on again a 60th of a second later for 50 to 100 microseconds, and does the same thing, turns off, and does the same thing right here. So when it turns off for about 16,500 microseconds. So the on time with the camera with the correct shutter speed or exposure is like less than 1% of the time. So then consider the LED or the light source that goes with that. Traditional LED systems called constant on, they stay right here. They're on all the time. That's problematic because it generates heat and it also wastes energy because the light is on when the camera is not on. So what you want to do is you want to develop a system where the LED turns on at the exact same time, very precise timing that the camera is taking the picture. And not only do we want to turn it on, we want to blast that LED with a tremendous amount, magnitudes more than you would ever do with constant on. So we talk about making silos versus shopping malls. And the amount of energy is hundreds of times more that we can get because we're only blasting that LED for a couple micro, and again, 50 to 100 microseconds, and then turning the LED off. That creates the amount of energy that we need to get through that steam. The other element is the way we construct the LED. This is a picture here, or not a picture. This is the actual chip on board that we use. 256 LEDs put on this board right here. Notice there are no reflectors on this board. This is just the chip right here. That has two distinct advantages as well. It's the way we focus the energy without having the individual reflectors on the LED. That allows us to mask the LEDs in one very, very tight area, then use a different technology called a Fresnel in order to focus the energy. And then number two, it's another thing you don't notice on this. There are no electronics on this chip whatsoever. So this is the LED built into the body right here. Notice the Fresnel lens right here. Fresnel lens is the technology they use in lighthouses. That is a completely even way to distribute the energy. And the way you focus it, it's the distance away from the chip or the chip on board that makes it a wide angle or a more narrow angle. But within that wide or narrow, it's perfectly even lighting. And we're going to show some examples of when you don't use Fresnel lighting technology, what that does to the camera's ability to collect resolution. In order, though, to have and use Fresnels, you can't use individual LEDs all over a board like a pancake. You have to concentrate that energy as tightly as you can. And the fact that it has no electronics means that this light head can survive with no air inside your dryer section up to 220 degrees Fahrenheit. There's nothing to burn. The driver and the power supply are remotely located. So this can live in that environment without air. So many times we go to paper mills, the light's out. You know why the light is out? Somebody disconnected the air. Somebody disconnected the water. And they don't know until days or weeks or months later of why that has occurred. We want to reduce that failure point by developing something that can withstand the environment, even in less than ideal circumstances. Another one, notice the front face. It's completely smooth for silicate glass so that it can be wiped down. There's no bevel on the glass. And also, if you want a water fall on this, you can clean the light that way as well. So you got to realize it's not just the technology. It's the way you house the technology. It's the way that you deliver the technology. It's also the way that you have to make the technology survive in these conditions in the paper mill. That's the legs of the kitchen stool. Any one of those goes out, the system fails, does not provide the uptime that we need to get the resolution to the operators. Therefore, operator utilization goes down. So one last point on this one. We've already talked about if you can answer all of these things and get all of this right, there's still another significant challenge in the paper industry that is above the steam, above the temperature, above the resolution that we provide. And this one is also specific to NIR. Turns out that NIR energy is monochromatic. We use a wavelength of about 850 nanometers. White light is not monochromatic. It has all of the visible light that we can see inside of what it projects out. So what happens when you take a monochromatic light source, send it up to a brown board, and then that reflects back to a black and white camera? What happens is that brown board, because it's being hit by monochromatic light, then bounced back to the black and white camera, appears white to the chip. Creates a much higher degree of contrast, which then means that images that would normally be dark with a very good, maybe, even if you get the strobing right, you get the chip right, you get the Fresnel light right, and you use a white light, you're not going to get the performance that you're going to get out of a near infrared, given the same amount of energy and the same setup. There's one example we'll show you later on here, and that is in a basement section where you may be up to 30 feet away from what you're trying to look at, and you may be looking at 280, 300 inches wide sheet. Traditional systems have multiple LEDs down there, just a whole bunch of electronics already and roasting and dying. With the NIR technology, examples will show you, one light was able and is able to give you enough of that correct energy so that the camera, most importantly, can operate at the correct shutter, correct depth of field, and correct contrast. Anybody can put a camera in a closet and give you pixels. It doesn't matter. It's the quantity of it's not the quantity, rather, it's the quality of what we give you. So we want to give you both. Quality is defined by depth of field, shutter speed, which is stop action clarity, and then lastly, contrast. Contrast being the darks look dark and the brights look brighter. The other problem that you get into if you don't have the right light, and we talked about this before, what do cameras do when they operate in poor conditions, when they are light starved? And I'll show you the examples, but to talk about it here, there's three distinct things happen when you don't have enough light. You can still produce an image. You can have a 3 million pixel image of nothing but blur because the light is not there. Number one, there's no contrast because you have to bump up the gain, which is an artificial aspect of what you do. Signal to noise ratio is then suffered because you have the noise, more noise than you do have signal. So the image quality goes down significantly. Number two, you have no depth of field. That means that cameras on the outside of the machine, there's no way to get focus on the middle or even maybe the back edge if there's one position versus what's on the front edge because your iris is wide open and you cannot get focus. If you can't get focus on the item, what do you think that dot or that defect or that blemish is going to look like? Well, you're not going to see it. Operators aren't going to see it. Your vision system isn't going to see it, whether it's a web inspection system or whether it's a proactive sheet condition alarm. It's like it was never there. And it gets worse. The third thing is that if you don't have shutter, then it's going to be a blurry mess. It's going to be a blurred image of a blurry moving object because the sensor isn't turning off and on fast enough so that the motion or the defect actually moves while the camera sensor is on. Like if you were to swing a golf club and you took a picture using 1/60th of a second technology, you wouldn't even see the end of the golf club. It would just be a blur for 12 to 24 inches, like it wasn't even there. So for the next one, let's talk about some images. So in closing, for this part of the presentation, 4 things to review that we talked about. Near IR has the right wavelength to deal with the steam, shorter wavelength of light. Number 2, it's monochromatic. That means that it's able to reflect a better level of energy to the types of cameras that we all use that are sensitive in the type of nanometers that we're building this chip on board in. So that gives us double advantage on that. Number 3, none of this works. None of it, unless you know how to hammer drive the LED in a way that produces the maximum amount of energy so that the right energy can hit the object and then bounce back to the camera. Number 4, none of this has any value unless you can make it have the even, we talked about melt, maximum even lighting on the target. It's the Fresnel technology that gives us that. And then number 4, if the LED cannot survive in the environment, doesn't matter about the wavelength, doesn't matter about the fact it's monochromatic, doesn't matter about the hammer, whatever, it doesn't work. All is lost. So you've got to address each one of the funnels of the technology or the legs of the kitchen stool so that at the end of the day, you can walk away from your system and know that day in and day out, it's providing the information that your operators need to drive that tool as best as possible. This is an easy one. This is a system that is not our camera, not our computer, not our software. It's the existing whole setup. We went in and added the LED light to it, and that's the exact same image given the right energy for the camera, all right? Tremendous difference. This right here has no value unless there's a truck that drives through it versus what we have here. Existing non-ECS camera with an ECS LED. Another example here, this is what we talk about, maximum even lumens on target. This is not even. So this is what happens when you use individual reflectors on your LEDs is it has a very, it's very powerful, but it's like a narrow. It doesn't do any good because you have to light up a much larger square area. So you're not getting much here. Again, same camera with an ECS LED. That's what your image should be looking like, night and day. These get a little bit harder right here. Right? This one is smart camera, 2.6 megapixel images. It's a lot of pixels. It's using a huge LED on here. This would have been the best technology before we came out with the 256 NIR. We used to have the 60 NIR. So what we're talking about today is a much bigger, more powerful array. So this right here is a white light. This is the back side of a very large Brownmore machine in the press section. So this is as good as you're going to get with traditional white light. This is the same one with NIR. Same camera, same everything. We just pull out the white light that we use and put in an NIR. This is the type of performance increase you should expect in areas that you could not see in before. Notice you can start to see even the felt line up there. If you can see that level of detail in the felt line, imagine the detail that you can see on your paper machine in the worst of environments. This is a dryer section. It's a great image. This is even using, again, a white LED. Look at the depth of field. This is a 200 to 300 inch machine. Notice I can see with one camera from front to back. Now, that's a factor of the type of camera that we use, the type of way that we set it up. But this is still with a white LED. So I would consider this to be almost an outstanding shot on its own. But it gets better when you deploy the NIR technology. This is that same image with NIR. You're able to see more into the sheet. The more you can see into the sheet, the more you can understand what your problems are, either proactive or reactive. This is a pickup suction roll. Pretty good image, outstanding shutter speed, got decent depth of field. So out of the 2, maybe 3 legs of that triangle we talk about, this has got just about all 3 of them. It's a good image with a white light. If you use a near IR light, it's the same thing right there. Which would you rather use, A or B? Notice the shutter speed on that right there. You're actually seeing the fabric right there that's coming apart, that piece of string that you can see kind of hanging down. This is a press section. Again, very, very good image. Notice the shutter speed. It's phenomenal. It's a great image, but it's using a white LED. Now, what does it look like using an NIR LED with the exact same settings? Look at that. You're getting better penetration into the sheet so you can see more issues that are occurring, not just on the edge. Notice the sheet appears whiter to the camera. So this is about towards the end. This is the same thing we talked about before. All right, so basement shots have always been challenging. You're very far away, light decreases by the square root of the distance. So if I'm 1 foot away, it's so bright. If I'm 2 feet away, it's a quarter. And if I'm 30 feet away, it's 1/30th, or there's a number, and it's not even that. It's exponentially less light. So when you have cameras in basement sections, you're running them with open shutter. You have no ability to have stop action clarity. you have no depth of field, so things are going to be blurry as they move across the image. And then number two, you're going to gain the camera so much that it's very hard to see what's going on. It'll look like a snowstorm because you're running the camera in a starved light environment. The solutions are you add a whole bunch of white LEDs down there, tremendous, like runways of them, or use an NIR LED that is a 256 built in a way to give the type and right kind of lumens so that the camera can operate in its best state. That is, with a closed iris of some sort to create the depth of field, with a shutter speed in the 50 to 100 microsecond range, without increasing gain. So you can do this first two. Yeah, you're thinking you're going great. And then you increase gain. Guess what happens when you have steam and you increase gain? The effect of steam is a million times worse when you mess with the gain. So you got to be able to run the camera without cheating. And the cheating is when you bump up the gain, because you're going to lose something when you do that. And you will lose visibility. So in the wintertime, when you're running that paper machine, you think everything's great in the summer, come the winter, can't see anything. There's a couple of things that are probably going on. But I bet you gain is one of the things that was used in order to get the image right when there was no steam. Gain is not your friend. So this is next slide is the 300-inch paper machine where I'm good 20 feet from the image. I'm even off to the side. I'm not directly under. I can't be because it's got oil, we got paper coming down. I'm going to be off against to the wall. So I'm even further away at an angle, which means depth of field is really important. I'm not perpendicular. I'm off to the side. So how do I get you the best quality pixels possible for proactive and reactive troubleshooting on your paper machine? It's this right here. You have to use an NIR light, where I happen to use a smart camera technology. So there's a pair technology that we have here, but you don't have to use our smart camera technology. You can use the existing cameras that you have because they all have sensitivity in the areas that we're using the NIR light. So 280-inch machine, and you can see right there the name of the felt and the felt line all the way across in clarity. That, folks, is producing the camera's best behavior to then deliver to your operators the best information that they can possibly have in order to drive that asset as good or as best possible. A couple other examples. This is on a trim squirt, a lot of steam, nothing there. NIR, you can see the trim squirt. Another pickup suction roll. The top one actually has poor shutter speed as well because the white light just doesn't give enough oomph in order to get you the shutter speed that you need. With NIR, sometimes we have to turn the exposure to an area because there's too much light, even close down the iris. Another example of a trim squirt. This is an easy one. This is just an existing system that had a white LED, traditionally fairly low power. Just it wasn't built very, very well. You come with their existing camera, put a better LED, in this case an NIR, that's the same image. But look at the information you can get out of that just by changing out the light. That's it. Put a better light on there. Worthless to worthful. So what did we discuss today? Starting with the end, we had some pictures at the beginning of very steamy paper machines, images from actual camera installations. What is near infrared? What wavelength is that? How does it work? How does using this type of lighting technology increase the performance of your vision system? I hope we've been able to explain that, as well as the mechanics behind that and what I call the technology funnel. If you remember anything, it's that at the end of the day, we want to provide your operators a better tool because they are the ones that have to drive that tool. When is it most ideal? It's ideal in every paper grade, from tissue to brown board to bleach board. I happen to show examples today on brown board because the monochromatic nature is very effective there, but the reduction of steam is important in any grade of paper that you make. Additional mill, we also showed more pictures of examples from the wet end all the way to the basement. What is the cost? So this near infrared light in the 256, which is our newest light, it's our biggest light. It's got the most LEDs shoved in there. It's anywhere from $5,000 to $7,000 per LED. And that includes the driver and the power supply. And can it be used on non-ECS systems? Absolutely. Most of the images you saw in today's presentation were not on our own systems. Some of them were with our smart camera. A lot of them were not. So we know how to do that marriage between most competitive systems from the camera that gives the heartbeat. So our light knows when to turn off and turn on. So we love to come in, do a quick audit, and show you how on your existing system, even NIR lighting can change the overall way that your system is working and the information that it provides.